Chapter 31 Physics, Theory Video 3. So stellar radii, that is, we are going to figure out how the radius of a star can be figured out. So first we are going to look at the sun. The sun, of course, we can figure out its diameter by using a very simple pinhole camera. However, the other stars and other celestial objects, we can't actually that easily figure out the distance of because they don't actually appear as disks up in the sky. But if you look at the sun, it will appear as a disk, and as a result, we can figure out its distance or its diameter by using simple principles that we can develop in relation to trigonometry. So here what we do is we we develop a pinhole camera. This is something that you have learned before O levels. So what happens is we take a shoe box, then at one end we create a small pinhole, a small hole, and then on the other side we place a tray, we place a screen. This should be usually a movable screen. So then on this screen, through the light, when it comes through the pinhole, an image of the sun would be seen on that screen. So we use the distance between the sun and the box, and also between the box, one end of the box and the other screen. We get these values, and using simple trigonometry we figure out the diameter of that. So the simple equation is going to be tan theta is going to be d upon x, where d upon which is equal to d upon 1.5 into 10 to the power 11. So then we get d to be equal to d is the diameter of the sun. Then we have d equals 1.5 into 10 to the power 11 into d divided by x. So I hope this makes sense. Then using this value you can figure out that is the image of the d, simple d. As you can see, the size of the image of the image that is seen, and then x is the gap between the pinhole side and the screen. So if you calculate that, you can figure out the diameter. So this is not something that you should be able to do, but rather explain how it is done, and then do the calculations based on the values that have been given. So you will have to do question number 6 before you move on to the others. Write down a note. The diameter of the sun can be calculated by using a simple pinhole camera. At one end, a sheet of darkened paper or aluminum foil with a tiny hole made with a sharp pin is present. Through this, light would enter and a circular image of the sun would be formed when it is pointed towards the sun. By measuring the distance x between the pinhole and the screen, and taking the diameter of the image, we can calculate the diameter of the sun using trigonometry. Tan theta equals d upon x, which is equal to d upon 1.5 into 10 to the power 11. So we remove the tan theta part, then we get d equals 1.5 into 10 to the power 11 into d divided by x. So what we have done here is we have simply taken these two and cross multiply. I hope it makes sense. Now we are going to move on to Wien's displacement law. Now you have seen that in a gas cooker, if the if you take wood a wood stove, what happens is when you start burning firewood, because the heat generated by the firewood is low, the flame is going to be red, dull red color. If the heat is higher, it will become reddish orange, and when you take a gas cooker where the heat is really high, it becomes white as it gets hotter. So this actually has this is the same for stars as well. The hotter stars have a bluish red color, white color. Then the cooler stars are going to be a shade of red. So this a hot object like a like so these hot objects, like stars, we can model them as black bodies. So this is a imaginative or idealized object that absorbs all the electromagnetic radiation that falls on it. So as a result, it has a when it absorbs it, it has a emission spectrum, characteristic emission spectrum. Then that the emission spectrum will depend on its temperature, thermodynamic temperature. So this is this chart would show you this chart would show you the color of the star at different temperatures. If it is greater than 33,000 Kelvin, then it is blue. So etc. You have different temperatures and different colors that is shown here. So as you can see here, the wavelength is going to be the observed color of a star is related to its temperature. This is what is shown here. Then here it is going to be intensity against wavelength graphs for objects of different temperature. Intensity against wavelength graph. So I hope this makes sense. So the characteristic values, the characteristics that we can understand from this is, if the object for an object at a thermodynamic temperature T, the intensity against wavelength curves peaks at a wavelength lambda max. So it is the intensity is going to peak at lambda max. Now the features that we can understand from this is, the higher the temperature of a body, shorter would be its wavelength at the maximum intensity. Then the higher the temperature of a body, the greater the intensity of the electromagnetic radiation at each wavelength. So these are characteristic properties when it comes to these hot objects. So another development in relation to this thermodynamic temperature T of the object and wavelength lambda max at the peak intensity. This relationship was found by Wilhelm Wien, and we call this Wien's displacement law. Lambda max T is a constant. Lambda max T is a constant. So temperature uh, uh, the temperature T, the thermodynamic temperature T, when the wavelength max at the peak intensity is a constant. And this has an experimental value of 2.9 into 10 to the power minus 3 meter Kelvin. So the surface temperature of the sun is 5800 Kelvin. So as a result, we can calculate the lambda max value, which is going to be 5 into 10 to the power minus 7 meters or 500 nanometers. So at this, therefore, as a result, light of this wavelength would appear yellow, and we know that it is true for the sun. Write down a note before you go to the questions. Wien's displacement law. Different stars at different temperatures release different light of different wavelengths. When higher the temperature, more bluish it becomes, and lower the temperature, redness would increase. It has been shown experimentally that the intensity wavelength graph depends on the temperature of the object, and the intensity against wavelength curve would peak at a wavelength of lambda max. The deductions that can be made using above graph. So you'll have to draw this graph, pause the video and draw that graph, then you will be able to understand that. The deductions that can be made are: when the temperature of a body is higher, the wavelength would be the shortest at the peak intensity, peak or the maximum intensity. Then greater the intensity of the electromagnetic radiation at each wavelength. That is, when the temperature is higher, for each wavelength, there would be greater intensity of electromagnetic radiation. In Wien's displacement law, a relationship between the thermodynamic temperature T of the object and the wavelength lambda max at peak intensity is discovered. Lambda max T is a constant, equals constant. The experimental value of this constant is 2.9 into 10 to the power minus 2.9 into 10 to the power minus 3 meter Kelvin. By using this value, delta max for the sun can be calculated. Surface temperature of the sun being 5800 Kelvin, which would give us 500 nanometers, which is the wavelength of the color yellow. So using these values and using the details, please do question number 7, 8, 9. After doing that, we will move on to the Stefan Boltzmann law. So if we have properly understood this, it is not only the surface temperature of the star that the luminosity is going to depend on. It will depend on the physical size of the star. That means its radius is going to have a effect on that. So there is a super red giant star known as KY Cygni. It has a surface temperature of 3500 Kelvin, but it has a luminosity of 200,000 times. So our sun has a surface temperature of 5800 Kelvin. So this super red giant has a lesser surface temperature, but it has a luminosity of about 200,000 times more than our sun. So that means its large surface area would make it very luminous. So there are two factors that would define the luminosity of a star. Its surface thermodynamic temperature, of course the temperature would have an effect, but there is another effect by the radius as well. So this was developed by Joseph Stefan, which he used to define another expression for the luminosity L of a star. This is called Stefan Boltzmann law. So this law known as Stefan Boltzmann law was developed, and this is for the luminosity of a star. So the equation is L equals 4 pi sigma r squared t to the power 4. So the two key equations that we need to learn here are lambda max t equals it is a constant, and so as a result lambda max is inversely proportional to t, that is lambda max is directly proportional to 1 upon t. Then Stefan Boltzmann law is L equals 4 pi sigma r squared t to the power 4. This sigma is a constant known as Stefan Boltzmann constant, and it has a value of 5.67 into 10 to the power minus 8 watts per meter squared per Kelvin to the power 4. Now we can use these equations to figure out the radius of a star. So what we got to do is we use Wien's displacement law to determine the temperature T of the star. So that means we have to find out the wavelength lambda max at maximum intensity for the star. Then we determine capital T. Then we use Stefan Boltzmann law to determine the radius r of the star. Luminosity L of the star will be used in the as explained in the earlier session, where we use the radiance flux intensity. So now let's look at this worked example, then you will be able to understand it better. So the surface temperature of the sun is 5800 Kelvin, and the wavelength of light at peak intensity is 500 nanometers. The wavelength at peak intensity for Sirius B, a white dwarf star, is 120 nanometers. The luminosity of this star is 0.056 times that of the sun. Then the luminosity of the sun is 3.83 into 10 to the power 26 volts. Calculate the radius of the Sirius B. So we use Wien's displacement law to calculate the temperature of Sirius B. We know lambda max T equals, it is a constant. Then we because it is, it is a constant, means for both Sirius B as well as the sun, it is the same. So we know that sun has a temperature of 5800 multiplied by 500 nanometers lambda. Then we multiply, that is equal to T into 120. So then we can figure out T is 24,200 Kelvin. I hope that makes sense, because it's a lambda max into T is a constant. Then the lambda max into T on Earth, as well as lambda max into T on of the sun is equal to lambda max into T of Sirius B. So when we calculate that, we get T to be 24,200 Kelvin. Then we use Stefan Boltzmann law to calculate the radius of the Sirius B. We have 4 pi sigma r squared T to the power 4. Then we make R the subject, square root L upon 4 pi sigma T to the power 4. We know L, that is 0.056 times of the sun's luminosity. So we multiply that by 0.056, our sun's luminosity, divided by 4 pi is a constant. Sigma is a constant. It has a value of 5.67 into 10 to the power minus 8, multiplied by T to the power 4. We found the T value. Here they have used the specific value, 24,167 to the power 4, which is going to be 9.4 into 10 to the power 6 meters. So that means it is the size of our Earth. It is very hot, but because it is very small, it has a low luminosity. I hope you understood that. Please do question number 10 if you understood.